Hello, and welcome back. So we're here with day 4, 2022. This problem, um, essentially your input looks like each line gives you a pair of number ranges. And part 1 basically says if you plot those ranges out, on a line or something, you'll notice that some of the number ranges are completely covered by the other one. And it could be that the first number range is covered by the second, or it could be that the second is covered by the first. And the question asks, how many assignment pairs does one range fully contain the other? So um, yeah, I think this is fairly self-explanatory, so let's get into it. So as usual, we will grab our input, 4.txt1. We get a bunch of lines. We can parse out the digits. This is kind of what we usually do. We use quad D, which is a string that contains all the digit characters. And we do membership, membership partition, right tac. Right, I have to, and that gives us all these digits. Now what I'm going to do for this problem is for each one of these groups, I'm going to reshape them into a 2x2 matrix. And what this allows us to do is, we can say each matrix is a single pair of ranges, and then each row is itself a range. So it allows us to operate on each pair to find answers, and it allows us to operate on each range independently. So if I mix this, I get this matrix of size 1000 2 by 2. So the way you can think of this is that we have 1,000 pairs of ranges. Each pair is represented by a matrix, and each matrix contains 2 rows for the two ranges. And then these are strings, so I just have to do for each execute. And that gives us a numeric rank 3 array, which we will assign to P. Now, there are there are several ways you can approach this problem. The most efficient way is there's a way where you can do like segment intersection, where you look at each endpoint and you do like a series of less than, greater than comparisons. Like you can think of each one of these ranges as it has 4 elements. You could assign them to like A, B, C, D, and then it's like C less than or equal to A or something else. Anyway, I got sort of frustrated with all that. So if we look at our input, we can see that the maximum element there is 99, and the minimum element is 1. So actually, we can, this isn't the most efficient way to do it, but we can essentially like construct the entire range in memory. 1 to 99 isn't that bad. If the ranges were wider, then this wouldn't work. So we can construct the entire range in memory. And the way that I want to do it is I want to use what's called a bit mask. So rather than having a bunch of numbers representing, indices, I'll just have a Boolean vector with ones in the positions denoting the range. And then I can use Boolean operations like and to determine where they intersect. So how do we do it? Well, first we need to construct a range. And if we take good old iota and we do like iota 5, this just constructs a range from 1 to whatever your number is. If I want to construct a range from like, let's say 3 to 10, then the first thing that I would do is take the difference. In this case, we always know that the right element is greater than or equal to the left one, so we don't have to take an absolute value or anything. If we do a minus commute, this is guaranteed to be a positive number. We can add 1 to this because if you think about we're trying to construct an inclusive range from 3 to 10, meaning that it includes both 3 and 10, then we actually need 8 elements for that. Then we can do iota. We get a range from 1 to 8. And if we add the left element, then we get this range from 4 to 11. Now I could subtract 1 from this and it would give us the range from 3 to 10, but actually for this problem it doesn't matter. The important thing is that I have a range consisting of the proper number of elements, and it's going to be evaluated the same for each range. Now I can construct a bit mask out of this using a neat feature of Dyalog, which is that a lot of the functions have inverses that you can access with power operator -1. And so normally where this monadic iota underbar, it will tell you the indices of all the ones in a Boolean array. And if you take the inverse of that, it will take a sorted list of indices and produce a Boolean array that has ones in all those locations. So if I do, you can see that the inverse applies if I do where again, I get back my list of indices, right? So this inverse is a neat way to construct a bit mask out of a sorted list of numbers. Okay, so I have a bit mask, and actually I can apply this. I can reduce this on P. So this is reduce last, which means that we're operating on each row. Reduce will take the first argument on its left side and the right argument, or the last argument on its right side. So if I do this, I get a bunch of Boolean vectors. What's the size of this? So this is a 1000 row by 2 column matrix. If I mix this, then I get a rank 3 array again, and now it's 1000 matrices of 2 rows, 100 columns each. So the way to think about this is for each line in our input, we have a matrix. The matrix consists of 2 rows representing a bit mask for each of the ranges in that line. And the bit masks are all 100 elements long. When I did the mix here to put the bit masks all into a single array, zeros were concatenated onto the end where needed to make them all fit the same shape. But luckily, zeros in a bit mask is totally fine. So let's call this im. Okay, so now that we have our bit masks, we want to find, the problem asks us to find all of the lines where given 2 ranges, one range completely contains the other one. So if we can operate on each one of our matrices by doing rank 2, and if we do an and reduce first, basically I am applying an and operation between the 2 rows in each matrix. And that gives us this. And so now we have a single vector that represents the anding between the bit masks for the 2 ranges. And if one of the ranges completely contains the other, then when we apply and between our 2 bit masks, that should be equivalent to one of the bit masks in the matrix, right? If I had maybe I can do an example. So I have 0, 1, 1, 1, 0, and then the second row would be, let's say that the second row is 0, 0, 1, 0, 0, right? If I mix these together, oh, nope. If I mix these together, I get a matrix. So you can see just based on the bit masks that the top row completely subsumes or contains the other one. If I do and reduce first, then I get this Boolean vector, and you can see that the vector is the same as one of the rows in the matrix. So if I do, I can find the index of our ANDed together vector in the original matrix. So this is right tac index of, and this gives me an index of 2. And what this tells me is that the matrix that's, or the row that's totally contained is at index 2 in our original matrix. The way that index of works is if the thing that you're looking for is not in the left arguments, then it returns a number greater than the length of the array. So if I change this example, if I change this example to have a 0 in the middle, well, actually, this doesn't, all of our ranges are contiguous in the input, so maybe like this. So I have a range of the first two elements on the top and then the middle element on the bottom. And if I do and reduce first on this, then I get, a bunch of zeros. This won't be contained in our original matrix, so we get an index of 3. And so we know that elements where one range doesn't completely contain the other will have an index of 3. So if we apply this function that we have, rank 2 on the matrix we built, which contains all of our bit masks, we get this vector. And this vector represents the indices where the ANDed together bit mask falls in the original matrix. If we do 3 greater than this, then we get a Boolean vector where the ones basically represent matrices where one range completely contains the other. And all we have to do is sum these, and we get 536, which is the answer for part 1. So once you construct the bit masks this way, it's really easy to answer these type of queries. So, okay, part 2. Part 2 says the number of pairs that overlap at all, and how many assignment pairs do the ranges overlap. So for this one, it's just going to be basically if we AND together our bit masks, if there's any overlap at all, then there will be at least one value. There will be at least a single 1 in the Boolean vector resulting from ANDing the two bit masks together. So we can just do AND reduce first, again, rank 2 on our matrix, and we get this. And if we just OR reduce, this is along each row, this tells us which rows contain at least 1, 1. And we get a Boolean vector for that, and it's just a question of adding them up to get the answer, 145, which is the correct answer. So if we put this down, this is part 2. This is part 1. We constructed our matrix up here. So this is kind of our pre-processing work. And we parsed our input here. So, like I said, this isn't necessarily the most efficient way to do it. If the ranges were wider, the fact that we're using bit masks rather than numbers gives us some space savings. But obviously, if the ranges were like hundreds of thousands of items wide, then this method wouldn't work. But I think it's a neat sort of array-based solution to the problem without having to use like a lot of conditionals where A is less than or equal to C and B is greater than or equal to D or whatever. Yeah, so those are the 2 parts for day 4. Thanks for tuning in.